Hi, this is Valentine from Simplistic, and in this problem we're going to take a look at how to find the pH of an acid, a weak acid solution, and we're also going to find the CO3 2- ion concentration. Now what's interesting about this problem is this acid actually has two ionizable protons. So there's going to be two ionizations that are going to take place. So we'll take a look at them in a few minutes. But when we're trying to find the pH of an acid, whether it's a monoprotic acid or a diprotic acid, in this case this is a diprotic acid, the pH will essentially come from the first ionization. Okay, so let's take a look at that first ionization and calculate the pH, and then after that we'll take a look at the second ionization. So we have H2CO3 aqueous plus water, and that ionizes to give H3O plus aqueous plus HCO3 minus. So that is my first ionization. Okay, so let's call that we'll call that a little later on. Okay, so initially I have 0.050 molar of this and 0 of this. The change is going to be minus x of this and x of that, and then the equilibrium is going to be 0.050 minus x and then x and x. All right, so once we have that, then Ka1, notice carefully, we put a 1 out here. That means it's the first ionization, which means only one proton is coming off. So see, you have one proton still left out here. Okay, that is going to be equal to H3O plus times HCO3 minus over H2CO3. And we know that this is x, and that is 0.050 minus x. So if you plug that in, we get x squared over 0.050 minus x. Now Ka, we have to pull that from a table. Ka1 is equal to 4.3 times 10 to the negative 7. So then we have 4.3 times 10 to the negative 7 is equal to x squared over 0.050 minus x. All right, this point in time, we're going to assume that, excuse me, x is really small. And with that assumption, we're going to solve this. So we get x squared is equal to 2.15 times 10 to the negative 8. So x is equal to 1.46 times 10 to the negative 4. Now, if you actually plug this value of x in and divide it by 0.050, let's go ahead and do that. 0.050, sorry. Let's go ahead and do that on the side out here. So we have 1.46 times 10 to the negative 4 divided by 0.050. That is equal to 0.0029, and that is less than 0.05. So therefore our assumption is valid. All right. So that's the concentration of X, which happens to be the concentration of H3O plus ion in solution. So if we take the negative log of X, that should give us the pH, which in this case is 3.83. So that is the pH of this solution. So now the second part of the question is asking us for the CO3 2- ion concentration. As you can see, we don't have that in this equation anywhere. So what that means is that we have to take this species and we have got to ionize it in the second step. So that is the second ionization. So let's draw that out. HCO3 minus plus H2O. That gives us H3O plus CO3 2 minus. Okay, so now initially, what do we have for HCO3 minus? We have X, because that is what X came out to be. So initially we have we have 1.46 times 10 to the negative 4. Okay, And what do we have for H3O plus? The same amount. So I'm going to copy that over. So we have that. And what do we have for CO3 2 minus? Nothing. Then the change is going to be, this is going to dissociate by X, so minus X, and then H3O plus is going to go up by X, so plus X. CO3 2 minus is also going to go up by X, so that's plus X. So at equilibrium, we have 1.46 times 10 to the negative 4 minus X. We have 1.46 times 10 to the negative 4 plus X, and then we have X out there. And now the equilibrium constant, Ka2, because this is the second ionization, is equal to concentration of H3O plus times the concentration of CO3 2 minus divided by the concentration of HCO3 minus, which is equal to 1.46 times 10 to the minus 4 plus X times X. The whole thing is 1.46 times 10 to the minus 4 minus X. Now, this Ka2, we can pull that from a table, and that is equal to 5.6 times 10 to the negative 11. Okay, so turns out if we solve this problem, I'm just going to go ahead and write this out down here so it looks a little neater. So that is equal to this. Okay, at this point in time, turns out we can assume that X is really small because this is the second ionization. So when we did the first ionization, X was pretty small out here, and that X that was small was actually, we even checked our assumption, and our assumption was correct. So therefore, in this case, we're going to assume X is even smaller. And I want to make one note out here that this X is not the same as the X above. In fact, let's just change all this to Y. That way we're all not confused. So let's go ahead and put Y out here, minus Y plus Y plus Y plus Y, Y minus Y. And then this one's going to be plus Y minus Y plus Y, Y, and minus Y. Okay, so we're going to assume Y is really small, and that will be a correct assumption in this case. So this entire term vanishes because if it's Y is really small, then that becomes 0 and that becomes 0. So therefore it's this over this. Therefore that vanishes. So Y ends up being equal to 5.6 times 10 to the negative 11. And this is the concentration of CO3 2 minus in molarity. I hope that made sense. Thank you for watching.